There we go. Okay. Thanks for joining us on today's webinar. We have Dr. Rosa Dominguez-Faust with us today. Who's going to walk through a working paper, and we've gotten guidance from folks to be very clear and transparent about what type of work this is. So I want to reiterate, this is a working paper to present findings, additional findings and analysis of the environmental performance of trucks.
The conference has been muted.
And we want to indicate, this hasn't undergone any formal peer review.
The conference has been muted.
But it has.
The conference has been unmuted.
But it has undergone some fairly substantial informal peer review from industry and governmental colleagues. So a few housekeeping issues. We're going to do 30 minutes of presentation followed by about 30 minutes of discussion. And you are all currently muted, but we encourage you to ask questions through the chat feature on ReadyTalk. And we are recording this webinar. We won't attribute any of the questions to any of you as individuals. We'll just be answering them generally, anonymously. And after the webinar is concluded, we'll send an email with a quick survey link and a link to the slides that we used today and a link to the webinar recording in case you'd like to forward that to colleagues who couldn't be with us today. And I believe that's it for housekeeping. So I'll now turn it over to Rosa, and we'll get started.
Thank you, Paul. So this is an analysis of the environmental performance of natural gas trucks, and I'm going to focus on the carbon intensity because that's what we've been modeling mostly. I just want to remind everyone that I have a focus on long-haul trucks, but we will be speaking about other Class A trucks too. So if you want to move to the next slide. So we are estimating the carbon intensity of natural gas long-haul trucks, and for that we're using a life cycle analysis. There are many different life cycle analyses, and they apply to they have different scopes, they have different geographic scope, they have different purposes. In the U.S., we have several, like for example, the EPA uses its own models for the renewable fuel standard. For the LCFS, ARB uses California Grid 1.8, which is a 2009 version, I believe. Soon ARB is going to present an updated LCFS numbers based on a California Grid 2.0. Canada uses GHG Genius, and in this study, which has a national scope, we're using the Grid 1 2014, so that's the national grid. So the interesting thing about the 2014 version is that it has added a heavy-duty vehicle module. Before that, Grid and California Grid focused on light-duty vehicles. And if you wanted to model heavy-duty vehicles, then you had to do some tweaks in terms of vehicle parameters. But now the new grid is much easier to work with right now because it has these added modules. It also includes some other short-lived climate pollutants such as black carbon and organic carbon. And it has some expanded and updated parameters in the old pathways. However, it doesn't include a Shell old pathway yet. So just a brief review of the boundaries of its life cycle analysis. That's important because you have to define what you're including in your analysis. We're doing what we call a well-to-wheel analysis, and that includes well-to-tank, two components basically. Well-to-tank, which is from the oil and gas fields to the vehicle tank, and then tank-to-wheel, which would be in-vehicle emissions. In GREET, in addition, you can split the well-to-tank into the feedstock segment and the fuel segment. Feedstock segment would be procurement of crude oil and natural gas, and the fuel segment would be converting this feedstock into a fuel. So that would be refining, transporting, liquefying, or compressing in the case of natural gas. So that distinction is going to be relevant. It's going to be important to the results I am presenting there. So the question is, are NGV trucks less carbon intensive than diesel trucks? And the answer is, it depends. So there's several parameters that we need to define. We make it's a modeling study, so we have to make assumptions, and those assumptions depend on the geographic scope. For example, like I said, parameters that apply to California don't apply to other states or are different from the national average. We're using the national average. And we're also making some assumptions about upstream methane leakage. We also make assumptions about the vehicle type in terms of the fuel economy and the methane slip of this vehicle, which are really, which as we will see, are very relevant. The global warming potential of methane is also an important parameter because that's how we weight the warming potential of methane. In that case, as I will explain, we'll use the 100-year global warming potential with the new numbers, which is 30. And then it will also depend on whether we use low heating values or high heating values for the fuel. In GREET, everything is low heating value. So I just want to make this clear. So I'm going to talk about the methane leakage. So the EPA, based on EPA and EIA data, the current estimate of methane leakage over the entire natural gas supply system is between 1.2 to 1.5%. Now, there's been lots of studies that contest this number, that don't agree with this number, and estimates range from it's 0.5 to, in some cases, as high as 8 or 10%. Okay. Now, there was this study by Alan Brandt from Stanford, which basically he compilated 20 years worth of research studies and concluded that it is the likely range of methane is between something between what it is now and 2.9 at most. Okay, so why the discrepancy between the official estimates and the expected more reasonable number of most 3%? Well, there are a few operators that are responsible for the majority of emissions, and that's what we call the super emitters, that are probably not included in the EPA inventory. And then there's also been proof that abandoned wells are still leaking natural gas, and those are not included in the inventory. So based on the inventory, where is the methane leakage occurring? In the GREET, we have a total estimate of 1.14%, and is split between production, processing, transmission and storage, and distribution, right? So we see that about a third of it is in transmission, another third is in distribution, and another third is in production and processing. Now, the vehicle type also has an influence in the results. As I said, I was focusing on long-haul trucks, and that makes me make assumptions about the fuel economy and the methane slip. And but I've been using the default in GREET after consulting with some industry experts, and we feel that these numbers are pretty accurate. So for diesel, we're using a 5.9 miles per gallon fuel economy, and for natural gas, we are giving it a penalty of 5% to the more efficient natural gas HPDI engines, and a penalty of 15% to the spark ignition natural gas engines. In terms of methane slip, natural gas, which is basically the methane in the exhaust, natural gas vehicles have substantially larger methane slip than diesel. Now, talking to industry representatives, we've been told that those numbers might be a little higher, so something like half of it, of what I'm showing here for natural gas, might be more reasonable. As I will show later, that will have some significant impact. And then I will review other types of Class A trucks, such as short-haul buses and refuse trucks. So another assumption that's important to remember is the physical properties of natural gas and methane. So the 100-year global warming potential of 30, and then a low heating value of both natural gas and diesel. So what does all this mean for the carbon intensity of natural gas trucks? This graph is showing the total carbon intensity measured as grams of CO2 equivalents per mile driven of diesel trucks, CNG spark ignition trucks, LNG spark ignition trucks, and LNG compressed ignition trucks. The colors are indicating the different segments in the life cycle. Blue is the feedstock procurement part, orange is the fuel procurement part, and gray is the in-vehicle use. The other thing that this graph is showing is the different gases. We don't see N2O because it's basically negligible, but we see CO2 in solid colors and methane in stripes. So the first thing that this graph tells us is that natural gas vehicles that use spark ignition engines have a higher carbon intensity than diesel trucks. The only natural gas vehicle that has a lower carbon intensity is the more efficient HPDI, it's a compressed ignition dual fuel truck. The other thing that strikes is that the majority of the emissions happen in the vehicles, not only CO2, but also methane. And that tells us that engine efficiency and fuel economy in general are very important parameters. The other thing that we can see is that in the case of natural gas trucks, there's a significant vehicle portion that comes from methane. That's the methane slip. So if we could reduce methane slip, as some manufacturers suggest, then this might drop a little bit. But I think it will be around what diesel is or above. The other thing that we need to see in here is the difference between CNG and LNG. If you look at the two middle bars, how the blue and orange is distributed. So for CNG, you see a larger chunk of emissions happen in the blue part, in the feedstock part. And that is because you're using transmission and then distribution to transport the natural gas to a refueling station where you compress it. And then you don't need a lot of energy to compress it, and that's the orange part, which is dominated by CO2 because it's CO2 coming from energy use. In the case of LNG, the feedstock part is as important as the fuel part, not more. And that's because for LNG, we're using the transmission line, and that's how we assume it. We're using the transmission line to transport natural gas to liquefaction facilities, and then you liquefy the gas and then transport it to the refueling stations by truck. in both these cases, we see that the CO2 emissions are larger than the methane, and that means that it's the energy processes, the energy-intensive process, what dominates the carbon intensity in the case of LNG. What I'm showing in this, in the next slide, is the carbon intensity as measured as grams of CO2 equivalent per mile for the 4 different tracks as methane leakage change. We're trying to test the sensitivities here to leakage, and also what we're trying to define is the break-even leakage rate. The leakage rate that will provide a carbon intensity parity with diesel. And that will depend on 2 things, the engine type and the storage type. And what we see here is the diesel line is a dashed line. The LNG with spark ignition is the green line. The LNG with the compressed ignition dual fuel HPDI is the purple line, and the compressed ignition and the spark ignition with CNG is the orange line. So what we see here is that the break-even leakage rate is around 0 or below, so no tolerance for leakage when we use the spark ignition engine. And we can tolerate up to 3% leakage if we're using the HPDI engine. The other thing that this graph is showing is how CNG is much more sensitive to leakage than LNG, because this increased, this added use of distribution, local distribution, which is leaking, unlike in LNG. So I think this is just a summary of results, so we can move to the next slide, which I just explained. And then what I want, of course, this is a modeling analysis. We do our best, but a model is just an imitation of reality, so there's some limitations in this analysis. What if leakage is higher or lower? What about biogas? And we're doing only long-haul trucks. What about refuse trucks and buses, others that can be? So in my next slide, I'm showing the percentage change in carbon intensity of long-haul trucks compared to diesel. So instead of the absolute number, this is a percentage change. And I'm showing 0%, the accepted current, or official, I would say, 1.14%, the 3%, which is the upper limit that we think is tolerable, and 10%, which is like an extreme case. And then in the last block, I'm showing renewable natural gas from landfills, assuming there's a 1.12% leakage. So what this shows is that at any leakage rate, really the only good performing natural gas engines have to be at the HPDI or similar, high efficiency NGV trucks. Because if you are using a lower carbon fuel, which is not like natural gas, in a less efficient vehicle, then you're basically losing all the benefits. But there's a way to do it better, of course, with renewable natural gas. And if you were to use renewable natural gas, 100% renewable natural gas, in any of those engines, you would obtain 70 to almost 80% reduction with respect to diesel. And that's for long-haul trucks. How does this look for short-haul trucks? Very similar examples. Wherever there is a high efficiency natural gas engine, we see the same pattern. And the only thing that changed here is the assumptions about fuel economy and methane slip of these vehicles. Then what I'm showing next, it will be the difference when you use refuse trucks. What happens here is we don't have a compressed ignition version of refuse trucks. So at least there is not in the model. So that doesn't mean it couldn't be done, right? But that's not a reality. So we don't have any advantage of using natural gas in refuse trucks unless we use efficient vehicles. Same thing happens for school buses. And again, what changes here is the assumptions about fuel economy and methane sleep. But for the most part, at current leakage and above, we don't have much benefit. We will need to use renewable natural gas. So now I'm going back to long-haul trucks. What percentage of renewable natural gas do we need at any given leakage to sort of offset the detrimental effects of this leakage? So I'm testing landfill gas in this case, although we have also, as you know, wastewater treatment biogas and also other waste, biogas from other organic waste. But if we use landfill gas, then we have that for the current 1%, around 1% leakage rate, we will need to blend about 10% renewable natural gas in the pipeline. In the case of 3%, that will go to 20% blend. And in higher cases, the higher you go, the higher the blend. So another limitation of this analysis is that, of course, we're using the national scope, so it lacks granularity, and it's not good for site-specific analysis like the LCFS. The main differences with the LCFS results that we're all familiar with are, however, the different functional units, where the LCFS uses grams of CO2 equivalents per megajoule, we use grams of CO2 equivalents per mile. So in one case, it's the low carbon fuel standard, it's the carbon intensity of the fuel, and we are comparing the carbon intensity of transportation. In addition, the LCFS numbers are going to need revision because they are based on an older version of the California grid that didn't have any shale pathways, didn't have drilling or fracking emissions, no methane leakage, lower global warming potential numbers for methane that are not used by the IPCC anymore. However, there is a new California grid that was just released yesterday for comments, and that will produce different numbers. And the timeline for these new LCFS numbers is early next year. So I played a little bit with this California grid. I'm not showing numbers because I haven't played with the very latest version they released yesterday. But my conclusion is that it's not the leakage rate like many people think, what makes the numbers different. It's other factors that affect upstream emissions. One of them is the distribution distances, the transportation distances of the fuels, which is basically a result of where they come from. So the oil mix and the gas mix are different for California. That the oil and gas that comes from California comes from different places than oil and gas that's coming to the U.S. as a general. The other thing is that in California there's a lot more renewable electricity. So the energy used in upstream processes is less carbon intensive. And another thing is that we have tighter air quality standards for stationary sources, and that has which is intended for NOx and PMs and whatnot, but has the co-benefit of less carbon emissions too. So the leakage rate is similar, but it's these other upstream factors that make all fuels in California less carbon intensive. So natural gas will be less carbon intensive, oil will be less carbon intensive too. And this is basically my take-home point slide for the U.S. NGV trucks only better than diesel if equal or better fuel economy. whenever we don't have this high efficiency engine option, natural gas will be worse. The majority of emissions happen in the tank to wheel, that's in the vehicle portion, so improving fuel economy and reducing maintenance slip is key. The well-to-tank CNG is dominated by leakage, whereas the well-to-tank LNG is dominated by the higher energy input. The break-even leakage rate is 3% for HPDI trucks and around 0% for SI. So zero leakage tolerance for spark ignition engines, and up to 3% we can tolerate if we use higher efficient engines. At current leakage rates, we should be mixing a 10% renewable natural gas blend to offset the leakage. And like I explained earlier, in California, all fuels have a lower carbon intensity. The leakage rate is the same. CNG could be better than LNG if compressors use renewable electricity, but vehicle fuel economy is still key. And with that, I'm finishing the presentation. I would just like to acknowledge some of the scientists that I have consulted with, although they don't have any, liability for these results. Robert Harris from EDS, Adam Brandt from Stanford, and Andy Burnham from Argonne. And I also want to acknowledge our team: Amy Jaffe, Daniel Schittrum, Nathan Parkin, Andy Berg, Hank Bing, Allen, and Lynn Zhu, and outside collaborators like Bob Harris and Kev Medlock for it's a group that we have produced a series of studies that those are a sample of what's been published recently. As many people know, the white paper on natural gas, this working paper on the carbon intensity, other analysis on natural gas resources, on vehicle cost, and similar studies that we've done. So with that, I want to thank everyone, and I think we can open it for questions. I think it's exactly half an hour. Great.
Yeah, okay, great. Thanks, Rosa. I see a number of questions here already. We'll start going through them in the order they were received, and I'd encourage you all to use the chat feature to ask additional questions. So first off for you, Rosa, we have a question here about methane feedstock. So why is the feedstock methane loss so much higher for CNG, and is this something that better compression equipment could help handle?
No. I mean, better compression equipment can improve. I mean, better efficiencies are always desirable, but the reason why the feedstock methane loss is so much higher is because, as I explained, this feedstock segment includes transmission and local distribution, right? So in LNG, you only include the transmission part, not the local distribution part. And since there's a lot of local distribution that leaks, that's a substantial reduction in the feedstock carbon intensity.
Okay, another question here about carbon intensity. Why is LNG so much lower than CNG? And where do we assume
that's exactly is the same question, so I guess I need to make that more clear. It's so much lower because we are sparing the leakage from the distribution lines, the local distribution lines.
Sure, that's right.
Okay. Clarification question here.
And that's because we're assuming the supply chain is transmission to a big, central liquefaction plant, and then transporting to the refueling stations by trucks. If we were to assume a sort of LNG in a box technology, where the natural gas goes through the local distribution lines to the station where it is liquefied, then we will have a higher feedstock carbon intensity there.
Okay. Clarification question on our use of California GREET 1.8. Could you just clarify whether methane leakage
Okay.
was included and
Yeah,
the
okay,
rate at which it, its rates and the importance of that particular rate included in California GREET 1.8.
Yeah, well, the California GREET 1.8 was the 2009 version, and leakage then was not as high as it is now. So there was some leakage, but it didn't have it wasn't as, by working, I mean, that's something that you learn by working with the model. It's not as evident. In the current GREET, you basically have somewhere when you can manipulate you can change the leakage rates to do this test, where before it was not as clear, let's say. And yes, they were much lower than that, because most of the research has come in the recent years. We have to think that this California GREET was it's like a 2009, I believe, so it's many years ago.
Okay. All right, good question here about the potential impact of alternative fuels like renewable diesel in diesel engines, and how would that compare to using renewable natural gas?
Yeah, we haven't analyzed renewable diesel. That's a good question, but we haven't gone into that yet, because there's many different pathways, and second, it's the indirect land use changes and stuff could be it's a little more tricky. And so I don't know, someone who does biofuels on a daily basis could probably answer that question. I have no idea how it will result in terms of carbon emissions.
All right, a fairly technical question here we may have to take offline, so we'll respond to the person who posed the question. And let's see. Another fairly technical, long question. Good questions coming in about this. Obviously, GREET gets pretty complex with.
No, we can actually
you
answer.
Want to tackle this
yes,
one?
yes.
Okay.
I mean, so this is a question about the fuel economy assumptions of the engines. There's no data reference provided for the 15% efficiency reduction. Well, I mean, that's hard to believe. I am basically, but I mean, you're right in one way, because I'm basically using the GREET defaults, and GREET normally documents everything, but this new vehicle module, the documentation is still not available. However, from talking to natural gas and diesel engine manufacturers, I could confirm that was pretty accurate. So I guess I could find a reference somewhere.
Mm-hmm.
We'll find it for the paper for sure.
Okay, and then another question about our statement that diesel is less carbon intensive than natural gas in California, and then another question regarding use of GREET 1.8, and then newer versions of GREET.
Yeah, I would like to remind everybody that the LCFS is using a different functional unit. It's using grams of carbon per megajoule. And so that's the carbon intensity of the fuel. And I think I've been saying all the time that the carbon intensity of natural gas is lower than diesel. It is when you use less efficient vehicles that you lose this benefit. So I think that's I understand how this is sort of frustrating, but for many people. But the truth is that we're using different units. I mean, you're using natural gas definitely has a lower carbon intensity than diesel. But then if you need to use more of it for the same miles, then you end up emitting more carbon.
All right, a question about recent reports from RFF and EDF. Are you familiar with these reports?
This is the recent report from okay. I think they're pretty much in good sync with the data here. So the thing is that I don't know exactly I don't know the exact leakage rate, but I've tested what we think is happening right now, the 1.14, a higher bound of the possible range, which is 3%, and I have also tested 0% leakage rate. So even if EDF and RF come with much lower leakage rates, I've tested the 0%. So they will be within my numbers. The results are not going to change because I'm already testing the 0%.
Good question on what work is being done to capture that methane that's being leaked.
What being done? Yeah. So we have there's the Natural Gas Start program by the EPA. That's a program that's been going on for a few years now, and it's sort of a voluntary sort of subscription. Companies throughout the supply chain can subscribe, and then what they get is assessments and monitoring by the EPA. They measure the leaks. They have this infrared camera technology and other technologies. They measure the leakage, and then they have a list of technologies like green completion and low bleed pneumatic stuff that they can use, and they have the prices. And based on how much the natural gas sells for, they give you an idea of what your payback period would be to implement these technologies. So with I believe it was with a $4 per million BTU, most of the technologies have payback periods underneath 3 years, and some of them were as short as 3 months. So lots of companies have sort of subscribed to this program, but what we have seen is that it is more likely that big companies that have better expertise, more tradition, are more likely to adhere to this program than smaller operators that are relatively new to natural gas production. And those are the more likely to be the super emitters that we were talking about. So I think the difference between a voluntary program that we have now with these natural gas start programs and a potential regulation that would make all operators use this technology would make a big difference.
Yeah. And I'll just remind our webinar attendees that Rosa and Amy presented a good slide on all those potential technologies and payback periods as part of our first webinar in this series of 3 webinars. So those slides are up, and maybe we'll include them in this deck for the second webinar so you can see everything in one place. Okay, a couple questions on what engine manufacturers we've spoken with. So and you'll have to remind me, don't break any of our NDAs that we may have signed with folks, but can you indicate who we chatted with, or at least if they were major engine manufacturers?
Yeah, how many do you think there are? Do you want me to say? Okay. So I had the Cummins, Westport in particular has been very useful, and like I said, Westport provides lower numbers for methane slip and also slightly lower differences in engine efficiency. I think those are fair, and what I'm seeing when I test those is that the numbers don't change much because it's not a big difference to what we have. So to answer that particular question, or to someone who's very concerned about that, if I use the numbers that I got from Westport, the analysis doesn't change much.
And I'll just add too, from a programmatic perspective, so for the STEPS program, Sustainable Transportation Energy Pathways, we have established relationships with other truck and engine manufacturers as well. I mean, there aren't too many, but we have a unique opportunity to, compare results across engine and truck OEMs. Okay, the next question is, does the fuel economy difference that we referenced represent city, arterial, and highway driving? What's the drive cycle use?
Yeah, and I would say, I don't know, it's like mixed. It's like we have to assume an average for everything. I don't know. I think you can have higher efficiencies at some points, but then that's, I don't know, it's just mixed use.
Okay,
It's long haul. I mean, it's going to be mostly highways, right? I think I wasn't answered this right. For long haul, we have basically highway cycle. For short haul, we will have city cycle. Same for refuse and same for municipal buses.
Okay. All right. Another good question on landfill gas. How much is in California, and if the gas isn't captured in landfills, does it leak to the atmosphere anyway?
Yeah.
And if you could harvest liquefied landfill gas, should you get a carbon credit?
Well, I've showed my results with landfill gas, and yes, definitely you get a carbon credit because you get a 70% reduction with respect to diesel. How much there is exactly, I don't have the number off the top of my head, and the way the baseline in grid for landfill, the baseline use for landfill gas in grid is flaring. So that's how the credits are estimated, how much carbon emissions you aren't producing by, instead of flaring this gas, you have, you are destining it to natural gas as a fuel for vehicles.
Okay, and question on the engine manufacturers. Did we chat with SI engine manufacturers?
Yes. Like I said, I talked to Westport, and they provided slightly different numbers for both fuel economy and methane slip. And with their numbers, with their numbers, the natural gas performance looks a little bit better, but it's still not enough to make a difference, a significant difference. It's still, I can show, I can do these numbers with the thing is that if the data people provide are similar to the defaulting grid, I prefer to leave it to the defaulting grid.
Okay, what was the, can you go back to that question, Connie?
The fuel economy of the fuel truck?
What was the source data for landfill gas?
Source data for the landfill gas.
Mm-hmm.
What do you mean? The source data for the landfill gas figure is the grid.
Maybe they're asking which version.
The grid is the same, the 2014 grid, one version, the national grid.
Mm-hmm. Okay, what
10%
fuel?
compared is about, yeah, but 10%.
Here, let's tackle this one.
Okay.
What fuel economy difference was used for long haul versus short haul, and how were those differences substantiated?
Yeah, I would have to go to the model because I can't remember off the top of my head. I understand I should have written it in the slides, so I can go back to the model and check and write them in the slides before we distribute because I can't remember exactly.
Okay. And then a reminder for folks here of the global warming potential you used, and how would results change if you had used the 20-year GWP?
The 20-year, yeah. So it would show natural gas vehicles much worse because it's basically emphasizing the short-term higher climate impact of methane over CO2, right?
All right. And then, I think this is fairly substantially covered. Keep questions coming in, folks, if you have any more. But why do you think this research was fairly surprising to some?
Because the LCFS, of course, gives natural gas a 20% advantage over diesel and gasoline. And I still agree to this difference in the fuel, in the carbon intensity of the fuel. I think what been striking is that when you put this fuel into use and you're using vehicles that are less efficient, then you basically you lose most of this advantage.
And what are next steps with this research?
Next step is trying to do the same analysis with the new California grid that was released just yesterday, and clarify all these questions that people may have in the working paper, and try to submit for publication.
Mm-hmm.
And for that, I mean, we're still always. I'm really open to comments.
Yeah, speaking of that, there's a question about how much this working paper has already been peer-reviewed. And the opportunity to do so is now, essentially. So I encourage anyone who's interested with these questions or questions that haven't been posed yet to reach out to Rosa.
So this paper was first distributed to our sponsors who had about 2 to 3 weeks to review it before we posted it online. And as it is posted online now for a month, we've been receiving a few comments, and we're still open for peer review. So whoever is interested, we're happy to see. We're not interested in being right. We're trying to be accurate. So if any comments that can make this study better and more accurate, it's fine. But for me, what I want to point out, and I think it's sometimes a collective mistake, we're looking at the absolute number. And I'm a modeler, and I know absolute numbers depend very much on the assumptions, which I've been trying to disclaim. And for me, what's important, the real insights that we gain from the models is the sensitivities. What can we do to make it better? So if someone tells me, no, the fuel economy should be this, and methane slip is that, that's great. And then I will show what these numbers will be with the new assumption. So I'm always open for comments. There will be there will be an official peer review process for a scientific publication, but this is an unofficial peer review process.
Yeah, and let me clarify just a little bit. So for papers like this, we distribute it to our STEPS consortium members, which not only include 20 some odd sponsors, but dozens of environmental NGOs and other governmental energy agencies and air quality management districts, and essentially anyone who's playing and interested in the space of alternative fuels, vehicles, infrastructure, policy, business decision making. So we really, in some ways, this informal peer review process is more substantial even than some journal formal peer reviewed processes, in the sense that we send it out to some 600 contacts, and they all have an opportunity to provide comment. Of course, we've definitely recognized that the journal peer-reviewed process is an end goal for much of this research, and we try to pursue every piece of research that's a white paper, a working paper, we try to pursue publication in a journal. So this is sort of an initial public release to interested parties, and as Rosa mentioned, we gladly accept comment, and shortly she'll be looking to publish this in an official journal.
When they accept it, yes.
Yeah, when they accept it. Which, another reason we like to do release of some preliminary info is it takes a long time to publish in journals. So we like to get the word out on interesting findings to add to the discussion happening for business and policy decision making. All right. Maybe we'll take a few more questions as they roll in here. Can you briefly explain the biogas cycle? If it's not captured, is it flared or released? And how does this impact the biogas greenhouse gases?
Yeah, so the renewable natural gas that I was using is basically landfill gas. And yes, the assumption is that if it's not used for transportation, it's being flared. That's the sort of minimum management they do. They do not assume it's leaked or used for electricity.
All right, and then a clarification on a question that I may not have addressed correctly. So on the landfill gas figure, does the leakage
We can go back to that.
add up to 10%?
Let's
Yeah,
go
what
back
slide
to
was that?
go back, this one, the curve. Is it this one? Let's ask if the person refers to this one.
Yeah, so we're going to try to respond to this clarifying question. We're
Well,
showing,
I'm gonna
up to 10% leakage, so can you
Oh,
speak to
I
why?
was asking what should up to 10%. No, this is not 10% leakage at landfills. Sorry, this is leakage rate in the system, in the entire natural gas distribution system. And yeah, 10 is a big figure, is extreme. I mean, we're seeing the reasonable estimate of overall leakage in natural gas systems is from 0 to 3. And what I was trying to show in this figure is how much renewable natural gas with its carbon credits can compensate for the leakage that's happening in the natural gas system, in the fossil natural gas system. In other words, what blends of natural gas with renewable natural gas are required. And if we assume that fossil natural gas is leaking 3%, you need 20% of renewable natural gas to be blended in order to sort of compensate. And the source of data for this is, again, the grid. Is an analysis performed with the grid, the national grid.
Okay. And another question about part of our review process so far. Have air districts been involved? I know they've certainly been invited. Have you received comments from Californian air or other air districts?
Yes, air districts are requesting that we do the California-specific analysis.
Okay, well that looks to be near the end of the questions, so I think we'll, pending any final questions, we'll go ahead and conclude for today. I want to thank the many of you that attended this, and again, feel free to reach out to Rosa. Here, I'll go back to her slide with her email address on it. Feel free to reach out to Rosa with follow-ups. We'll be having a third webinar in this series with date to be determined, but that will be our collaborator down at Rice University, Dr. Ken Medlock's study on national natural gas supply and what that means for natural gas supply for the state of California. So very relevant work, very interesting work, and we'll be having that webinar here in the coming month or so. Any final thoughts, Rosa?
Yeah, so there's one final question about the multi-city study released yesterday on transmission and distribution leakage. That would not change my results for one thing. What they're finding is that the distribution system leakage rate in these cities in 2011 is lower than the EPA inventory from 2011. We're using more recent EPA inventories which already have lower leakage rates. So, and like I said, I've already tested the zero leakage scenario, and that doesn't have seem to have a big impact. So, you know, more leakage is bad, less leakage is only a little bit better. I guess that's...
Okay, so good. Thanks for tackling that question that snuck in there at the end. So we will compile a log of these questions, and I'll ask that Rosa follow up with anyone that we may have missed or anyone that asked a particularly technical question. Most of them were about GREET. And then again, feel free to reach out to Rosa. We'll have our third webinar in the series in the coming weeks. And thank you all very much for your time today. Bye-bye.
Bye-bye.